Alrighty, so here we are in chapter 6 still dealing with random variables, and we're going into section 6.2, transforming and combining random variables. And again, this is taken from the stuff that's ready for me in the Practice of Statistics resources, which is awesome. All right, so today we are going to learn how to describe the effects of transforming a random variable by adding or subtracting a constant and multiplying or dividing by a constant. We're going to find the mean and standard deviation of the sum or difference of independent random variables. And then finally, we'll find probabilities involving the sum or difference of independent normal random variables. The rules that apply to random variables when it comes to transforming and combining them is essentially the same set of rules that apply to transforming distributions, like data sets, which you should have seen, I believe, in chapter 2. All right, it's the same set of rules. We're just applying it to a new context. So first, in section 6.1, we learned that the mean and standard deviation give us important information about random variables. In this section, we'll learn how the mean and standard deviation are affected by transformations on random variables. Recall that in chapter 2, we studied the effects of linear transformations on the shape, center, and spread of a distribution of data. Right? When adding or subtracting a constant a to each observation, adds a to measures of center and location. All right? Adding or subtracting a constant does not change the shape or measures of spread. All right? Those will stay the same. Come on. Clickety, clickety. Come on. All right. Multiplying or dividing each observation by a constant b multiplies or divides measures of center and location by b. It will also multiply or divide measures of spread by the absolute value of b. Right, measures of spread are essentially measures of distance. Distance isn't negative. You can't go back in time kind of thing. So we use absolute value of b to measure how far away we are from certain things, or what the distance or spread is, right? We use absolute value. And again, the shape will not change. All right? So let's look at some examples. Essentially, we're going to use the same example throughout. Pete's Jeep Tours offers a popular half-day trip in a tourist area. There must be at least 2 passengers for the trip to run, and the vehicle will hold up to 6 passengers. Right? We're going to define x as the number of passengers on a randomly selected day. Right? So x can have values 2, 3, 4, 5, or 6. Those are the only options. We can't have half a person. So this is a discrete random variable. Right? The probability of having each number of passengers is given here, 0.15, 0.25, 0.35, 0.20, and 0.05. And then we have our histogram of the distribution as well. All right. Calculating the mean, we get a mean of 3.75 and standard deviation of 1.090. We're now going to transform our random variable x to give us the amount of money collected. We're going to call that random variable c. This is also a discrete random variable. It has specific values attached to it and specific probabilities for each outcome. Pete charges $150 per passenger, which means for 2 passengers, it's 300, 3 is 450, 4 is 600, and so on. The probabilities of each of these amount of money being collected is the same as the probability of having that number of passengers. Right? That probability just carries over. There's no new calculation to find that probability. Right, so we get that. And then, yay, awesome. I'm glad you can hear now, Nathaniel, Nathan. Notice our histogram of this distribution is the same shape as the previous one. Shape did not change. We are multiplying by a constant, so shape stays the same. And based on what we know with distributions of data, the fact that this is essentially just carrying over to a new context, the mean is found by multiplying the mean of x. The mean of c is 562.50. And because we're multiplying, that also affects the standard deviation in the same manner. And we multiply 1.090 times 150 and we get 16350. Right, so these concepts that worked in distributions of data also work in random variables. All right, so that's good news. We don't have to learn a new set of rules. This works the same way. Going to move it on. And to summarize that, the effect on a random variable of multiplying or dividing by a constant, we get multiplying or dividing each value of a random variable by a number b, multiplies or divides measures of center and location, mean, median, quartiles, percentiles by b, and multiplies or divides measures of spread, range, IQR, standard deviation by absolute value of b. Does not change the shape of the distribution. And again, as with data, if we multiply a random variable by a negative constant b, our common measures of spread are multiplied by the absolute value of b. Once again, that's because essentially measures of spread are measures of distance. Distance isn't negative, it's just how much it is. So then, considering the same context, we're still looking at the amount of money collected. We have that same probability distribution and the histogram and the mean and standard deviation from the previous slide. Now, we're doing a second transformation. We are subtracting amount of money because it cost Pete $100 per trip to buy permits, gas, and ferry pass. Right, so the random variable V describes the profit Pete makes on a randomly selected day. Why they chose the letter V and not P, I don't know, but there you have it. So the profit could be 200, 350, 500, 650, or 800. And again, these are all essentially measures of location. We just subtract the $100 from each of the previous values, 300, 450, 600, 750, 900. We get these ones, all right? And probabilities transfer over again. They're not changing, it's the same. If I had 2 passengers, I collected $150, I spent $100, I made $200, right? Probability still carries. Once again, we see basically the same histogram, same shape, right? It's shifted to the left 100 units or $100, right? So we took this whole stack and just pushed it over, right? And because all we did was shift this to the left, the measures of spread don't change, right? The distance from 300 to 900 is the same as the distance from 200 to 800. Right? I didn't do anything to adjust those by subtracting. So that means the mean of V is 462.50, just C, the mean of C minus 100. However, the standard deviation remains the same, right, at 163.50. Right? The subtraction has no effect on the measures of spread. Is there anything I can clarify about this so far?
I have a question.
Mm-hmm.
How did you get the standard deviation of 163.50?
For the money collected or the profit?
It's the profit.
So so we can look at what the calculation is if you'd like. So remember, our standard deviation is always, oops, oh no, stop. Sorry, I forgot to lock my desk in a standing position. And it started moving. So remember, the calculation for standard deviation is your observation or your outcome minus the mean squared times the probability of that outcome happening. And then we add each of those up. So in this case, right, let me get my drawing thing here so I can scribble around on this. Show you stuff. Let's get a pen. That'll work. So, like for example, for our first measure here, right, we would take 200 minus the mean, 462.50, squared times 0.15. right? And then we'd add the next one, 350 minus 462.50 squared times 0.25, right? And we'd continue till we get to the last observation, 800 minus 462.50 squared times 0.05, right? And this would be the calculation to find the variance, right? So this would be that, right? This gives us the variance. We take the square root of this, we get our standard deviation. Now, the reason this is the same as this, because 200 minus 462.50, this number here, right, that's negative 262.50. If I go up to this one, 300 minus 562.50 squared times 0.15. 300 minus 562.50 is also 262.50, right? So we get the same exact set of calculations on this lower probability distribution for the variance as we do on the upper one, because our distances away from the mean of each outcome is the same between the two probability distributions. And that's why the standard deviation or the measures of center or measures of spread don't change, because we took, thinking of the graph, we took this whole graph, this whole histogram here, right? And we just moved it down 100. How spread out it was didn't change. We didn't adjust the width of the histogram. The only way to adjust the width is by multiplying or dividing. So then, to sum that up, the effect on a random variable of adding or subtracting a constant, right? Adding the same number, a, which could be negative, right? Which essentially, when you subtract 100, you're adding negative 100, to give it that way, to each value of a random variable. This will add a or subtract a to measures of center and location, mean, median, quartiles, percentiles, but does not change measures of spread, range, IQR, and standard deviation. And that's because of the reasoning we just showed. All right. And again, it does not change the shape of the distribution, which we saw by just comparing the histograms. So then, between multiplying, dividing, adding, subtracting, we have linear transformations. Right? The effect on a linear transformation on the mean and standard deviation, right, are given below. If y equals a plus bx, which is why we call these linear transformations, it looks like the formula for a line, is a linear transformation of the random variable x, so we're taking x and transforming it to y, then the probability distribution of y has the same shape as the probability distribution of x. The mean of y is equal to a plus b times the mean of x. Right? So this is accounting for the fact that adding, subtracting, and multiplying, dividing affect the mean, both of those things. The standard deviation of y is equal to the absolute value of b times the standard deviation of x. Right? We use absolute value again because b could be a negative number, and we can't have a negative outcome for the standard deviation. Right? And again, this illustrates that we only need to worry about whatever's being multiplied or divided. We do not need to worry about adding or subtracting when it comes to standard deviation or measures of spread. Okay. So linear transformations have a similar effect on other measures of center or location, median, quartiles, percentiles, and spread, range, and IQR. All right. So these are the other measures of center and spread that we're not considering at this moment in time. We're just dealing with mean and standard deviation. But these transformations have the same effect on these other things. Whether we're dealing with data or random variables, the effects of a linear transformation are the same. All right. These results apply to both discrete and continuous random variables. So if we're dealing with discrete, which our example was discrete, or continuous, which we haven't seen an example of continuous in this context yet, same rules apply, right? You're gonna treat it the same way we did the ones in the example, to move from one mean to the next mean, or standard deviation to the new standard deviation of the other variable. So that's linear transformations. We're going to now move on to combining random variables. All right, so many interesting statistics problems require us to examine two or more random variables. So we're going to investigate the result of adding and subtracting random variables. All right, we can always add or subtract random variables. Whether or not we can do other things after that depends on a couple other factors. We'll talk about those today. All right, so we're going to let x equal the number of passengers on a randomly selected trip with Pete's Jeep Tours. And then y is the number of passengers on a randomly selected trip with Aaron's Adventures. All right, Pete and Aaron are siblings. They live in other different parts of the country. That's just some other context of the problem that was not provided. We're going to define t as x plus y. All right. So in other words, t is the total number of passengers between both tour companies on any given randomly selected day. What are the mean and variance of t? There's a reason why we're doing variance and not standard deviation. We'll talk about that in a moment. So here's our data for Pete. It's the same set of data we saw earlier. Same mean and standard deviation. And here's our data for Aaron's Adventures. Notice Aaron can only have between 2 and 5 passengers. The fact that they're different sizes, so to say 2 to 6 and 2 to 5, does not affect us being able to add the random variables. You don't need to have the same size sets. Right? It just changes the number of possible outcomes since they're not the same. And then for Aaron, we have a mean of 3.1 and a standard deviation of 0.943. And we have our histograms here as well. So here we are. How many total passengers can Pete and Aaron expect on a randomly selected day? Again, remember, if you see this word expect, that's asking for the mean. The other thing we call the mean is the expected value. Okay, since Pete expects a mean of 3.75 and Aaron expects a mean of 3.1, they will average a total of 3.75 plus 3.1 or 6.85 passengers per trip. We can generalize this result as follows. All right. For any two random variables x and y, if t equals x plus y, so we've defined the random variable t to be the sum of the two random variables, then the expected value of t is the mean of x plus the mean of y. Right. In general, the mean of the sum of several random variables is the sum of their means. Right. And this can be calculated longhand. It'd take a while, even with this few number of combinations possible. We'll look at that in a moment. But knowing the rule saves a ton of time. All right. How much variability is there in the total number of passengers who go on Pete's and Aaron's tours? All right, so we're now referring to how do we do the variance on a randomly selected day. To determine this, we need to find the probability distribution of t. So the only way to determine the probability for any value of t is if x and y are independent random variables. We call things are independent if knowing one doesn't change the probability or likelihood of the other thing. So if knowing whether any event involving x alone has occurred tells us nothing about the occurrence of any event involving y alone, and vice versa, then x and y are independent random variables. All right, so what's happening next only applies to independent random variables. If your random variables are not independent, meaning if you know something about one of the variables and that changes the likelihood of the other one, you cannot do what we're doing next. It does not apply. All right, probability models often assume independence when the random variables describe outcomes that appear unrelated to each other. All right, you should always ask whether the assumption of independence seems reasonable. In our investigation, it is reasonable to assume X and Y are independent since the siblings operate their tours in different parts of the country. Right, so if someone signs up for one of Pete's tours, it's not taking away the possibility of someone signing up for Aaron's tours. They're not pulling from the same population, so to say. All right. Is there any questions about this? Again, understanding independence and how it can affect our probabilities is important. We need to be able to decide if something's independent or not. So this table, all right, shows all the possible combinations of the values of X and Y. All right. And so this would be essentially what we would use to calculate the mean as well if we wanted to do so of all the possible outcomes. But we have a shortcut. We add the means and we get the same result. So what we're showing here is we could have 2 passengers for Pete, 2 passengers for Aaron, a total of 4 passengers. The probability of 2 passengers here and 2 passengers here is the product of the probabilities of having 2 passengers in each. 0.15 times 0.3, we get that probability of having 4 passengers. Notice that there's only one way to get 4 passengers, right? But we get 5 passengers in 2 different ways, 6 passengers in a couple different ways, a few different ways, and so on. Right? So this is showing each possible combination. So then if you were to put this into a table, right, your table would go from 4 to 11. All right, 4 would have a probability of 0.045, 5 would have the probability of 0.06 plus 0.075, right? So we'd add those things up, we'd get our whole table filled out if we wanted to do so. And that's what this probability distribution shows. Okay. So now why did we do this? We're getting there. So first, recall that the mean of t is the mean of x plus the mean of y, about 6.85. This totally makes sense. That looks to be about where the center of this distribution should be based on distribution, right? The variance, again, is the sum of the difference between the observation and the mean squared times the probability of that observation. So we can calculate the variance of each of this, right, random variable t, doing the same type of calculation I showed previously. And we get 2.0775, right? Now, the variance of x was 1.1875. Now, we weren't given that directly. However, if we squared the standard deviation that we had, which was like 1.0 something, we would get this variance. Same thing with the variance of y. We were given the standard deviation, square it. Now we have a variance, right? 1.1875 plus 0.89 equals 2.0775. All right. So that means when I'm adding independent random variables, right, the variances, right, if I want the variance of the sum of those independent random variables, all I do is add the variances of the random variables. But variances, not standard deviations. You cannot add standard deviations. All right, so that brings us to our result of this. As the preceding example illustrates, when we add 2 independent random variables, again, I'm stressing independent, that's important. Their variances add. Standard deviations do not add. Don't add them. Don't try to add them. They don't work that way. All right. For any 2 independent or random variables, x and y, if t is equal to x plus y, then the variance of t is the variance of x plus the variance of y. In general, the variance of the sum of several independent random variables is the sum of their variances. All right. So we have that. And again, remember that you can add variances only if the 2 random variables are independent, and that you can never add standard deviations. So again, this is being stressed. Please don't add standard deviations. Please only add variances, and only if those random variables are independent. So We'll continue. We can perform similar investigation to determine what happens when we define a random variable as the difference of two random variables. But in summary, we get the following. For any two random variables, x and y, if d is equal to x minus y, then the expected value of d is the mean of x minus the mean of y. In general, the mean of the difference of several random variables is the difference of their means. Remember, the order of subtraction is important. If d is defined as x minus y, then you have to subtract the mean of x from the mean of y. They have to go in order. In short, 5 minus 2 is not the same as 2 minus 5. Right? Order changes the results. You have to do them in the order defined. Okay. Variance of the difference of random variables. This is a little not intuitive. For any two random variables x and y, if d is defined as x minus y, then the variance of d is the variance of x plus the variance of y. In general, the variance of the difference of two independent or random variables is the sum of their variances. So whether we're adding or subtracting random variables, variances always add. Is not a typo. Variances will always add. So now we're going to look at combining normal random variables. Remember, if it's a normal random variable, it is continuous. So now we're moving from discrete to continuous. If a random variable is normally distributed, we can use its mean and standard deviation to compute probabilities. Hooray! Any sum or difference of independent normal random variables is also normally distributed. Right, so this is nice. Right? If we start with two normal random variables and we combine them in some way, we still have a normal random variable as the result. Right. So our example here, Mr. Starnes likes between 8.5 and 9 grams of sugar in his hot tea. Suppose the amount of sugar in a randomly selected packet follows a normal distribution with mean 2.17 grams and standard deviation 0.08 grams. If Mr. Starnes selects 4 packets at random, what is the probability his tea will taste right? All right, so to do this one, we define our random variable x to be the amount of sugar in a randomly selected packet. We're taking 4 packets. They all represent the same random variable, essentially. So then t represents the sum of 4 randomly selected packets of sugar. All right. The amount of sugar in those packets. So we have x sub 1, x sub 2, x sub 3, x sub 4. Right, and again, we use the subscripts to denote this was the first packet chosen, second packet, third packet, fourth packet. Right, we want to find the probability that t is greater than or equal to 8.5 and less than or equal to 9, so between 8.5 and 9 grams. So we find the mean, because we need the mean to start doing our calculations. Right, so the mean of t is the mean of each random variable, which essentially has the same mean, right? 2.17 4 times. We get 8.68. We then calculate the variance by adding the variances. Now, we weren't given the variance, but we know that the variance is equal to the square of the standard deviation. So we have 0.08 squared 4 times, adding the 4 variances. We get 0.0256. Right. But remember, that's the variance, so we have to go one more step and take the square root to get the standard deviation, and we get a standard deviation of 0.16. So now we have what we need to be able to perform our calculation. We have a normal distribution, right? T is normally distributed, and it has a mean of 8.68 and a standard deviation of 0.16. Right. We can use this information now. Down just to have it. There it is. Right, so t is normally distributed with a mean of 8.68 and a standard deviation of 0.16. Right, remember, this is our notation to say that something is normal, and we have the mean and standard deviation listed as an ordered pair. Then we do calculations. Right, this is a graph over here of the distribution. Right, showing the area under the curve that we're interested in. between 8.5 and 9. All right, so we're getting all this area. It's always good to have the normal distribution graph because it gives you a visual of the area you're looking for, right? If you got a result of 0.2, that would be a hint that you probably did a calculation incorrect because that's like easily more than half of the area under the curve, right? So it's a good visual cue to see if you're doing things correctly, right? In order to do this calculation, we need to standardize the upper and lower bound of our range here, 8.5 and 9. So we have a z-score for 8.5. 8.5 minus the mean divided by the standard deviation is negative 1.13. And for the upper bound of 9, we get 9 minus 8.68 divided by 0.16, we get 2. Okay, so we're then going to find the probability of z being between negative 1.13 and 2. So using table A, we find 2 on table A, we get 0.9772 as a probability, or the proportion under the curve to the left of 2. And then we get 0.1292 as the portion under the curve to the left of negative 1.13. So to get this probability, we subtract this one from that one, we get 0.8480. Meaning there's about an 85% chance that Mr. Sorensen's tea will taste right based on this normal distribution. Is there any questions on this example?
For the 0.8772 minus 0.1292, you got those answers by looking at the C table, correct?
By looking at table A, yeah. Yeah, so
okay.
Here, I can pull up table A here and show you. Let's get this a little bigger. So here we go. So what was our lower bound here? Negative 1.13. So if we look at our table, right, we go to negative 1.1 right here. So then we complete the decimal 1.13, right, by going to where the 3 is, which is the 0.1292, right? Then, right, the upper bound was 2.0. So we go to the positive side of table A. Sorry, I have other scribbles on here. And we find 2 right here, and it's just 2.00. So we go to the 0.00, right, and we get 0.9772. Okay, and now we know that we subtract the 0.1292 from the 0.9772 because of how the distribution looks here, right? Table A always gives me the proportion to the left of a given value, right? So from here over, the 0.9772 is a proportion to the left, all of it. So it includes this part here that I don't want. However, to the left of 0.113, right, from here over, is the part that I need to get rid of that I don't need from the other one. So that's why we subtract the 2. We get 0.8480. Okay, does that answer your question? Does that make it more clear?
Yes, it does.
Yay, hooray. All right, awesome. Is there anything else I can clarify? All right. And does anyone need a moment to write anything else down from this slide? All right. So then we've reached the conclusion, right? In summary, today we saw how to describe the effects of transforming a random variable by adding or subtracting a constant and multiplying or dividing by a constant. We saw how to find the mean and standard deviation of the sum or difference of independent random variables. And we just saw an example of how to find probabilities involving the sum or difference of independent normal random variables. All right, so that sums it up, guys.